Hey, so this lesson where we start to look at matrices is really the beginning of a field of mathematics called linear algebra. And we'll kind of delve into this a bit, and the ideas of matrices will come back in other units as well. For example, in the geometry in trigonometry unit later on the HL lessons. And we've worked with matrices a bit in probability, we just haven't really talked about them much. So anyways, a matrix, and the plural is matrice, but a single matrix is a collection of data represented in rows and columns. And so, for example, this matrix here has 6 elements with 2 rows and 3 columns. And in general, we define a matrix by the number of rows and columns, and by convention, we always have the number of rows first, so 2 rows and 3 columns. So this particular matrix we say is a 2 by 3 matrix. And when we refer to any part of the matrix, we call these elements. So this has 6 elements. We refer to first the row number in the column. So for example, this would be the element 1, 2, and this would be the element 2, 3. With that quick little intro, there's nothing inherently complex about a matrix, but as we delve farther and farther into this, there will be a fair amount of things to think about. So I have 3 matrices here, A, B, and C, and first the orders. And again, the order is a description of the number of rows and columns, always rows first. So the order of A is 3 rows by 2 columns, so it's just 3 by 2. Same thing for B, it's the same order, 3 by 2, whereas matrix C, I shouldn't say equals, I should say a colon, whereas matrix C is 2 by 3. So we do want to remember it's always rows first, then columns. So now I want to state the elements. And so element A32 refers to in matrix A, and by convention, if we see a lowercase letter here, that refers to the uppercase letter here. So matrices, by convention, we use uppercase letters to denote the entire matrix, and a lowercase letter to denote the different elements in it. And so A32 refers to the 3rd row in the 2nd column. So that's 0. So we'd say A32 equals 0. B12 represents the 1st row in the 2nd column. So right there, -5. And C23 represents the 2nd row and the 3rd column. So there's the element 3. Like I said, not difficult at all, just you want to make sure you have the correct order. And now finally, determine if possible what I get when I add or subtract or multiply these matrices in different ways. And it's not always possible. To add or subtract matrices together, they have to have the exact same order. And so I can add A and B together quite nicely. And how do I do that is just by adding the elements in order. So this element with this element. And so A plus B, my first element would be 1 plus 4, which is 5. And then 5 plus -5, which is 0. And just keep doing this. And notice if they didn't have the same order, then I wouldn't be able to add them up, because at some point there would be an element that doesn't match up with another. So doing this quickly, I should get these values. So the order will be the same. If I go B minus A, same idea. I gotta be a little bit more careful because I'm subtracting. But just, for example, the first thing I would do is I'm starting with B, so look at element 4 and subtract 1. So I'd have a 3 right here. And keep mine with negatives. Sometimes subtracting a negative, right, we have to, when that comes up, it's the same as adding, and I should quickly get these elements. And while later on we'll look at how we can use our GDC to speed up some of these things, honestly with just addition and subtraction, it's probably faster just to do it yourself. Now A plus C is not possible because they don't have the same order. It seems like you can get started, 1 and 7, okay, but then pretty quickly we don't have an element here, but we have an element here. And so you just cannot add these. So that's nice. And then finally, 2C. This just means matrix C times 2, quite literally every element being multiplied by 2. So in this case, 2C. Just be all those elements doubled. So 14, -2, 4, and so on. Right. Okay, so addition and subtraction, multiplication, with a constant with matrices. Quite pleasant. Like I said, just remember order is always rows and then columns. All right, so here I have a sum of two matrices as well as, what we get. So I have two matrices being added plus their sum, and I want to find the values of A, B, and C. There's a whole bunch of ways of doing this, but for example, if I just recall what we've just seen about matrix addition, I know 2 plus A must equal 2B. So 2 plus A must equal 2B. And I can see that 3 plus -1 equals 2. Well, that doesn't do me any good, but it's true. 3 plus -1 does equal 2, which is good. Over here, I have A plus 1 plus 2 must equal B. So already now I have two equations with two variables. I can solve the system quite quickly. For example, if I look at the equation I just wrote down, I can say A plus 3 equals B, or A equals B minus 3. Substitute that into the first equation I have, and I have 2 plus B minus 3 equals 2B. Pretty exceptionally straightforward system to solve compared to others we've seen. Solve for B, and you should get B equals -1. Which, to be honest, if you look ahead, you can actually see that in another way. -2 plus 1 equals B. Well, -2 plus 1 is -1. I can see that there. There's lots of ways of doing this. That said, now that I've found B, things are going to come together quite nicely. Now that I know that B is -1, substitute that there. I quickly get A equaling -4. And lastly, to find C, well, for example, I can see there's a C right here. And so 4 plus A must equal C. Keep in mind, A is -4. So therefore, C must equal 0. There's other ways of approaching it, like I said, but pretty straightforward. And again, in this case, just use a system quickly. Lastly, we will see more and more applications with matrices. This is the early stages of it. But I have a matrix here that represents the amount of toxic emissions produced by two factories, where element J represents the amount of toxic I released by factory J. Factor, I should say factory. I'm sure you don't care. That's it. Just so to be clear then, if I look at this matrix, that means this column represents one factory, and this is how much of some toxin it's releasing, and this is another. And this column here is another factory. So we do want to realize here that the columns in this case are the factories. And the rows here are the toxins. Some toxin, some other toxin. All right. With that said, though, the factories are required to reduce their emissions by 10%, which means I want to take away 10% from all of these. I can accomplish that by just multiplying everything by 0.9, finding 90% of everything. And so I can answer this by just finding 0.9 times A. There's my scalar. 0.9 times A will take away 10% and multiply all these values by 0.9. And when you multiply all these values by 0.9, you get, for example, 22.05 instead of 24.5. And then it's quite routine. I'm just going to do all the rest, and then we're done. I'm just literally multiplying every element by 0.9. Where things get challenging, and they will, is when we have to do more with this and where we have to, think more about how this can be manipulated in different ways. But for the starting point, I hope everything's pretty straightforward. Get a good basis on it, because things will get more challenging.